All right, today we are going to have our first plenary talk. And what this is it's going to be a series of talks where I have a theme. In this particular case, it's going to be how to dissect equations. And during these themes, I'm going to specialize and, pick out, in this particular case, one equation, which is going to be the trajectory of a particle. And then what I'm going to do is I'm just going to show you guys how to dissect the equation. What that means is, what are the questions that you should be asking yourself when you look at these equations? Or how can I study more efficiently for a physics test? Or even any other STEM class, or perhaps this will help you in other classes as well. But this is how I feel like I learned the most when I started physics. And so I'm going to kind of run through these things rather quickly um, and see where this goes and see if it helps you. So when we're talking about the trajectory of a particle, we're talking about the equation y minus y0 is equivalent to x tan theta, minus gx squared divided by 2v 2v squared cosine. Oh, that's cow. Cosine theta. I gotta square this, don't I? No, this is all difficult. Okay, so this is our equation, and that's a lot. It's a pretty big equation. So what do we have here? Sorry for the formatting issues. We have a few things. We have y, we have y naught, we have x, we have theta, we have g, and we have v naught. So what are these? I guess you could say the first question you should ask yourself is, what are the variables that I have? Followed by, what do they mean? So what is y? Y is the final height based on the time or horizontal position of the projectile. So now I've introduced a new word here, projectile. Some might say, well, what is a projectile? Or maybe it's rather trivial to some. But a projectile is any object that travels through the air or travels through some medium, most likely air, in the path of a parabola. And you guys are familiar with those because, in math, we learned y equals x squared is a parabola that points upward. Uh, so in this particular case, we're not so much focused on this relationship. We're going to rederive this relationship in a different way. And we can actually look back up here and say, oh, hey, here's our parabola. But before we continue, we now know what a projectile is, and we definitely understand what y is. So now we want to understand what y naught is. Y naught is the initial position or initial height based, or the initial height that the projectile is fired from. Okay, so that's fairly self-explanatory. We're usually given this, and we can usually make this 0, but sometimes it's a different number. This next variable x, we definitely want to know what it is, and that is the horizontal, x is the horizontal coordinate that the projectile travels. So if we were looking at a football being thrown through the air and we were to shine the light, or maybe we're playing during the day, so we don't need a light, we can see that the ball casts a shadow on the ground, and that shadow that's cast on the ground is the horizontal coordinate of that football. And so what's special here is x holds a very special place, and we're going to see why when we go to derive the equation for projectile motion. So before we continue, let's talk about theta. Theta is the initial firing angle measured from the x-axis or horizontal axis. So what's G? Everybody's familiar with G. G is the gravitational constant on the surface of the Earth. I know it seems redundant, but you should do these things and, just make it muscle memory. And so V naught is our final variable here that is inside our equation. And what we're going to do is, this is the initial velocity of the projectile when it is fired. Or let's say it is the initial velocity of the projectile the instant it is fired. It's very specific wording that we're choosing here. And so let's make this nice and fancy real quick, because I don't know. All right, so we have completed what I would consider the first part of dissecting an equation, and that would be defining all of our variables. Okay, so now what's the next part? How can we continue this? Well, the next viable question to ask ourselves is, what is the equation of a projectile, or the equation of projectile motion, or the equation of the trajectory of projectile motion? This ultimately is asking the question of, where does this equation come from? So if we think back to our equations for constant acceleration, I'm sorry, for constant velocity, we can pick up a few equations. We can pick up the position is equal to the velocity times the time in the x direction. So let's go ahead and label that velocity as the velocity in the x direction. And then we're also going to need the equation of the position equation for our y coordinate, which is given by the following. In fact, I think it will change that back to yeah. Got to be careful. Keep track of your signs. So we have these two equations, and we also need to understand that Vx is the x component of velocity, which if we have some initial velocity V naught, we can multiply it by our initial angle of firing, and that will give us our velocity in the x direction. And this velocity is actually, like we have defined, now it's the instantaneous velocity when the projectile is being fired at this given angle. So we can say the same thing and ask or not necessarily ask the same question, but look at the velocity in the y direction the same way. And if we think of it the same way, we have some initial velocity fired at the angle theta, and so that would mean that the y component of our velocity is the sine of that angle. So, where do we go from here? Because the question that we asked is, where does the equation for the trajectory of a projectile come from? Well, we have to understand something. We have to understand that when we talk about projectile motion, that the motion in the x direction it has a constant velocity. So what does it mean when something has a constant velocity? It means that there is no acceleration. So this means that there is no acceleration. So since velocity is a constant, that means that the only thing that changes in this equation when time changes is the x, or the x position itself. So if that's the case, we can actually solve that equation for t. And that's going to give us something pretty useful, because in this equation here, we see that we have time. We also see and can infer what Vy is. But ultimately, we need to be able to get rid of y, or get rid of t in this equation. So now that we have this definition of t, we can redefine this equation to have the following when we replace t. Okay? And so let's just go ahead and plug these values in as well. So when we do that, we're going to get okay. And now we can start to see how this equation is going to fall out and give us our projectile equation, or the trajectory of our projectile. So we can simplify this equation by plugging in here. I forgot this one. We see that we can simplify this further by canceling out these v naughts and remembering that sine theta divided by cosine theta is tan theta. So that gives us y equals y naught plus x tan theta. And here in this second term, we have g, we have x squared, and that's all divided by 2 times v naught squared sine squared. I put the wrong thing in here. Oops, I'm sorry. Look at that. See, I make mistakes as well. And so when I plug this in, I get our equation for the trajectory of a projectile. And so really that's how you dissect this. So how can I summarize what it is that we've learned? We learned how to dissect the equation by labeling all the variables and making sure that we understand exactly what those variables mean. We then asked ourselves where the equation that we're trying to learn about or dissect came from. And what that does is that leads us on this path where we can learn how the equation is derived. But before we can derive it, we have to understand that there is no acceleration in the x direction. That's what makes projectile motion so special. That's what gives us the ability to write this equation out. All right. I hope that this helped you, and I hope that you have a great day.